In cooperation with the services, combatant commands, and other DoD agencies, the Missile Defense Agency is developing and fielding an integrated, layered ballistic missile defense system. This system of indo- and exo-atmospheric interceptors, ground, sea, and space-based sensors, and geographically dispersed command, control, and battle management assets contributes to the protection of the United States, its deployed forces, allies, and friends against ballistic missiles of all ranges, and is adaptable to new 21st century threats. During this past year, we reached several milestones as we continue to improve the BMDS with technology upgrades, expand it with the help of our international partners, and demonstrate its performance using a robust, cost-effective test program that replicates and simulates operationally realistic conditions. For Homeland Defense, we continued to refurbish and upgrade the Fort Greely fleet of ground-based interceptors to ensure reliable operation, and we install the latest fire control software to allow testing or exercises to be conducted while simultaneously controlling the operational system. We completed major construction of Missile Field 2 and fully integrated the Thule upgraded early warning radar into the BMDS. As part of an expanding sensor network, the Thule and Fylingdales radars will provide an early view of in-flight threats from the Middle East and deliver critical surveillance and tracking cues to Homeland Defense assets. With the deployment of the Aegis ballistic missile defense ships to the European theater and the Antipi-2 radar to Turkey as a forward-based sensor, we met our end-of-year commitment to deploy initial regional defenses, or Phase 1 of the European Phased Adaptive Approach. We continued to deliver Standard Missile 3 Block 1A interceptors to provide a flexible sea-based missile defense capability against short and medium-range threats. More advanced versions of the SM-3 and upgrades to the Aegis weapon system will enable us to defeat even more challenging regional threats. Agreements reached with Romania and Poland to host Aegis ashore batteries were among last year's significant achievements and critical to our ability to meet Phase 2 and Phase 3 commitments under the European Phased Adaptive Approach. As part of this effort, we also commenced development work on an Aegis ashore test facility at the Pacific Missile Range facility in Kauai, Hawaii, which we expect to complete by 2014. We continued production of terminal high-altitude area defense interceptors for the first 2 THAAD batteries, which can defeat short to medium-range missiles inside and outside the atmosphere, and may be transported overseas as a unique missile defense surge capability. And finally, this past year, we continued to operate and sustain a worldwide high-capacity command, control, battle management, and communication network, which includes regional nodes in several combatant commands. Our C2 BMC network makes timely tracking information from sensors available to all interceptors in a region and manages complex and rapidly unfolding missile defense engagements. Although we have made very good progress in the development of missile defense technology over the past year, our most significant advancement in missile defense capability still lies ahead of us. Integrating fused data from a continuously available network of remote sensors with interceptor fire control systems to greatly expand the forward edge of our battle space and the range of threats we can engage today. A compelling glimpse of our future was demonstrated last April in the Aegis flight test FTM-15, when we demonstrated for the first time launch on remote in a ballistic missile engagement. We used an SM-3 Block 1A interceptor and sensor data provided by a forward-based Antipi-2 radar to intercept an intermediate-range ballistic missile over the Pacific Ocean, the longest-range missile ever destroyed by Aegis BMD. This step was the first of many taken to demonstrate the feasibility of networking remote sensors for enhancing missile defense performance. FTM-15 accomplished another BMDS first. We sent Antipi-2 cues to 2 space tracking and surveillance system satellites, or STSS, allowing them to acquire and track the target from space, then transmitting their data back to the BMDS. This demonstration showed the potential of launching an interceptor based on remote space sensor data. Last July, in FTX-17, we successfully tracked a short-range air-launched target using several remote missile defense sensors in California, including the Antifi-2 at Vandenberg Air Force Base and the Beale upgraded early warning radar. We again demonstrated with STSS that we could track the target from space and transmit data to the BMDS, where it could be fused with other tracking data sensors. In other tests, we conducted the first flight of the more advanced SM-3 Block 1B interceptor with the Aegis 4.0.1 fire control systems. While we did not intercept the SRBM target's separating payload, FTM-16 demonstrated critical system functions to include the exceptional performance of the SM-3 Block 1B kinetic warhead, which allowed us to move forward with the certification of the Aegis BMD 4.0.1 computer program. We have learned from the FTM-16 results and will repeat the test this year. Last October, FTT-12's successful operational test showed for the first time THAAD's capability to defeat 2 SRBMs launched in a raid scenario in their terminal phase of flight. In the future, if we are going to defeat ballistic missiles launched in large raid sizes, we will require adequate interceptor inventory and layered defenses. When missile defenses were used in February 2008 to destroy a large tank of toxic fuel on board an out-of-control U.S. satellite, MDA successfully leveraged tracking data supplied by several remote sensors with viewing opportunities of the satellite, which was traveling around 17,000 miles per hour. This geographically distributed sensor network included non-MDA sensors operated by the services and other national assets. Without this diverse remote sensing network, this one-of-a-kind intercept mission would not have been possible. Although it has been proven to be very effective against short and medium-range targets, when the Spy-1 is used as the sole sensor in a ballistic missile engagement, Aegis BMD capability is greatly enhanced when augmented with a network of remote sensors to engage IRBMs and ICBMs with the SM-3 Block 2 interceptors. One limitation inherent in many radars is the inability to see over the horizon or around the curvature of the Earth. This distance limitation is a significant physical reality when dealing with long-range threats which travel at very high speeds. By the time an extremely fast target object comes into viewing range of the Spy-1 radar, the window of time for launching an interceptor, which also has a limitation, its flight speed, is very narrow or may not exist at all, because interceptors have a limit on how fast they can travel and radars have a limit on how far they can see. We have a physics problem. In order to expand the space for potential engagement, our C2 BMC will respond rapidly to threat detection and passes tracking information to system interceptors in real time. In order to overcome the physics problem posed by fast-moving targets, we will also have the ability to give the shipboard interceptor a head start. We need forward-deployed remote sensors extending out near the ballistic missile launch point to act as first sight sentries and pass that early target viewing information into the system's C2 BMC for processing. Once this data is passed through C2 BMC to the interceptor on the Aegis BMD ship, which may be on station several thousand miles from the launch point, the Aegis weapon system can calculate the precise launch time. This will allow the ship to launch an interceptor even before its own Spy-1 radar can see it, to put the interceptor on the predicted path of the target to destroy it. In the future, our ability to defeat multiple ballistic missiles of different ranges by intercepting them in the ascent, mid-course, and terminal phases of flight requires we develop capability to enhance our view of the entire battle space today. In our FTX-17 test involving multiple sensors, we demonstrated with the STSS satellites we could leverage viewing angles from space and pass tracking information into the system. Precision tracking space system satellites currently under development will give us a persistent sensor capability to detect and track threat launches from regions of concern. As the ultimate remote sensor network with a continuous high ground view of objects traveling through space, a constellation of PTSS satellites will provide persistent, high-precision, real-time tracking of enemy ballistic missiles necessary to develop fire control solutions for the BMDS interceptors. Increased sensor networks are critical improvements the warfighter will need to conduct future missile defense engagements.